All right, so let's talk about our next part of the inference with one mean. Okay, so we're going to talk about the assumptions. Now, they're mostly pretty much the same as they have been and what we're aware of. So let's take a look at that. Um, so here we have, of course, random is going to be the same thing, that they are stated or assumed to be randomly selected from that population or randomly assigned to the treatment group. Okay. Independent, same thing. The sample size is less than 10% of the population. Now, remember in our last unit when we had proportions and there were two of them, we also had to say that they were independent of each other. Well, we're just with one mean right now, so that's not part of this because we just have one mean. Okay, large enough. Let's take a look at that. So our regular old large enough for means was that the sample size is greater than or equal to 30. So remember that the central limit theorem says if n is large enough, then it doesn't matter. The shape of the population, the sampling distribution's about normal. So we can then use those t distributions if we just have that sample standard deviation. But we are going to be having some situations where it might not be large enough. But there's still hope. So here are the next steps. So here's this, so for the first thing, is it greater than or equal to 30? Then bam, we're good to go. Nothing to worry about. Okay. But if that's not the case, then the second thing we check for is we go back up and reread the prompt to see, oh, had the population been told to us to be approximately normal? If so, then we are good to go, even if the sample size is small. Okay? Even if the sample size is small, if the population is normal, then anything that comes out of it, all the babies, all the sampling distribution babies are good to go. Okay. But here is kind of the new situation. So here we go. Let's take a look at it. If you have a small sample, but you go back up and you check the prompt, and they did not say that the population is approximately normal, then you're like, dadgummit, holy moly, what the heck now? Well, the third and final possibility to hold out for is, did they give you the individual pieces of data? For example, down here, see, did they give you the individual pieces of data? In this case, we just had however many that is, I don't know. Okay, so if we have the individual pieces of data, then we are going to, and I'm going to show you how to do this in a second, then we're going to make a little dot plot here. And I'm going to talk about all the qualities you need to have. And if we make this dot plot, and I mean, it's a small data set, so it won't be perfect, okay? We are essentially, see, and look, here's the second one. Is it perfect? No, it's a small data set, okay? But essentially what we're saying is there so much strangeness going on here that I couldn't possibly construe that the population it's coming from is approximately normally distributed? Or, so here's the things we check. Does this small amount of data look somewhat symmetric? And we're pretty liberal on what we say. I mean, what we allow. I mean, it would have to look way, way funky for us to really not go with this, okay? So is it somewhat symmetric? Is it fairly unimodal? Now see here, this first one here doesn't look like it, but I mean, if we had, even if we just had one more piece of data right there, then I would be looking a little bit more like unimodal, okay? And are there no outliers? So do I have a piece of data like way out here? Then I'm going to be a little concerned. Okay. But if it's sun. That's our little um, word phrases or our little thing that we're going to mnemonic device to look for. Is it somewhat symmetric, unimodal, and no extreme outliers or unusual features that are just blaring an alarm? Then I'm saying, oh, well, it's not too bad. So it is possible that the population that it comes from is approximately normally distributed. I don't have evidence to dispute that. So that's our final possible event that we can go through to go ahead and be good with this test, okay? Or this inference about the means. All right, that's it. So let's talk about the steps to do this. So here we go. So the first thing I do is I look at my data and I determine what is the range of that. So see, I'll come and I'll do, okay, highest value. So I'll scan my data and I'll see, okay, what's the biggest number and then what's the smallest number. Okay. So I know what the range of my data is. Okay. Then I'm going to decide what size I want my bins to be. You want to have approximately 5 to 10 bins. You're going to be more to the 5, okay? Because remember, these are going to be small data sets. So it's more likely that, you're not going to want to spread this out too much, or it's just going to look like a flat line of dots spread out across the range. Okay, so that's what I did next here. I said, okay, I take that 110, I divide it by 5, and that's like 22. And then I just kind of come up with, what's that close to? What does that sound nice that I could go by? So I'm going to make my bins 20. Okay, so there's the thought process. Now, then I come on over here and I draw my lines. And you will be freehanding this. So this isn't going to be something perfect, but this is a legitimate thing that could happen on an AP test. Absolutely. Free response. Okay. So I'm just going to draw my 2 lines and I'm going to make sure that I label. Over here on the left, these are going to always be your frequency because it's how many pieces of data you have. Okay. And I could label the 1, 2, and so on. I don't think it's necessary because we know that each piece of data is a dot, and that's standard, so we're okay. But label what the context is at the bottom. All right. Next, when I'm putting my numbers on here, you may do your little railroad tracks for the x-axis, but not for the y-axis. Do not railroad track this y-axis and then jump to 10 or something. Don't go railroad track here and then jump to 10. Okay, because that then violates the area principle. That makes some things maybe look like half as much as something else when they actually are not. Okay, so you can cut the x-axis, but not the y-axis. And so I did that here. So look, I railroad tracked it, and I started at 100 because my smallest piece of data was 120. Oh, 120. Did I have one lower than 120? Oh, I had one that was 100. Oh, so I actually had 100 here. Okay, so I wasn't perfect, but it still came out okay. So I had this 100, and then I went up by 20s because that's what I approximated. So there it was. And so then I put each piece of data, so 160, and so then I put it in this bin. So let's talk about how do you put this in the bin if it is exactly that on the line, okay? So if you remember from back whenever we did our little histograms and such, way back in September or October, then this needs to go to the right of that line. So see here, if we have 160 as this line, then this bin contains from 160 up to, but not including 180. The 180s would go in this bin right here, okay? So that's then how that happened. So my 160 was right there, and my 200 is to the right of that number 200, so that's right there. And 220 is right here, and so on. And then notice I'm kind of keeping these all level here. 1, 2, 3. So I'm keeping those frequencies so they don't violate that area principle. Okay, so then I put in all my data and I write out that it is sun, somewhat symmetric, approximately, or unimodal, and no outliers. So then the approximately normal model applies, and I'm good to go, and you go on from there. Okay? So why don't you stop and pause and try this second one yourself and see how that works. And then we'll do one complete example on the next page. All right, so pause and let's see how you do. All right, so with this problem, my top number was what, 1419. So here was my range. That's what I did. And the lowest was 1087. So that was about 332. I divided by 5 to see what that's. It's 66. So I was like, I mean, could I go by 60? Yes. I just decided to make it easy on myself because it seemed to be, it's a pretty big spread. So I went by 50s. You'd go by 60s, whatever. I just thought 50s is easier. So that's what I did. So is it possible that your dot plot could look a little different than mine? Absolutely, because you could have different widths of your bins. Okay, so yours might be a little different, but overall, it's going to be sun. Okay, so that you can see that. So label this here as miles. Did my railroad tracks right here, and then I started at 1,000, and then I went up by 50s, and I put in my data. Okay. And see, like this 1200, where did it go? Well, I can tell it went in this bin right here because here's 1200 and you go to the right of that. So, anyway, I don't know how yours came out because I don't know what your bin width was, but mine did come out to be somewhat symmetric, unimodal with no outliers. So, I'm good. I feel like I can safely say the population is not too funky that I'm worried about making an inference. Okay, so I'm going to go from there. All right, then here's our last one. So here we go. This is about Thomas Lane, a busy street where the posted speed limit is 30 miles per hour. I think it's actually 20. And I kind of go faster than 20 on that. And I've gotten a ticket on Thomas Lane before. Okay. But anyway, so the local police sometimes place a radar detector on the side of the road as the vehicle approaches. This detector displays the speed. Do you know those where you driving past and it'll show what speed you're going? Does that make you slow down? I don't know. Some people try to go faster to see how they're doing. But anyway, the police hopes that this will make drivers slow down if they are reminded of their speed. But the neighborhood residents are not convinced that this passive method is helping, so they wish to persuade the town to add extra police patrols. And I think they did at some point because then one of them told me they had a neighborhood person called and was upset about people speeding through there in the mornings. So I got a ticket. But anyway, so to encourage drivers to observe the speed limit to help their case, they randomly selected during a random chosen time of the day, and they did 23 randomly chosen vehicles. Okay, so we're going to go ahead and see, does this data give local residents evidence that the average speed of the cars going through the neighborhood is greater than that posted speed limit? So what do we need to do? What kind of inference do we need to do? A hypothesis test or an interval? Well, hopefully you can see that we want to do an interval. Wrong. We want to do a hypothesis test. It would say make a 90% confidence interval or something if you were going to do that. But so here we go. So I see I got individual data, so that's not good. Plus it's only 23. So when I see that, I'm like, ugh, great. This is too small because I know it's less than 30. But anyway, so let's work through that. Okay, phantoms. So notice we're putting the mean of the speed. So I did mu of S is the average speed in miles per hour of all such cars on Thomas Lane. The null hypothesis is that that average is 30. The alternative is that it is greater than 30. So here comes our conditions. We have stated that there are 23 randomly selected vehicles. I would certainly imagine 23 is less than 10% of all such vehicles on Thomas Lane. But darn it, look at here what I do. I write, is it large enough? No. 23 is not greater than or equal to, I should write that word 30 in there. And if I go back up and I read up here in the prompt, all of that, and it never said there's that the population is approximately normal. So poo. Okay, so therefore, I'm going to have to plot the data. So I go through that process. I found out what the range was. I divided it by 5. And so I decided to make each one of these about 3 miles per hour. So here was frequency label. Here is the speed. I did my railroad tracks and started at 20. So I did 20 up to that. And wow, that's great looking data. So sure enough, it is somewhat symmetric, unimodal, no outliers. So an approximately normal model applies and I'm good to go. So the name of this is a one sample t-test for means. Because, we have for slope later on this year, one sample t-test for slope, okay? Now, here's the other thing, is I need to get my t-score, my test statistic, my t-score. So to do my t-score, I need to do x bar minus the mean, the hypothesized mean right there of 30, and then divide it by that standard deviation, which that standard deviation comes from taking the standard deviation of the sample and dividing it by 20, the square root of 23, the square root of n. And I wrote that it's degrees of freedom 22. Okay, so in a situation such as this, you're going to want to, and I think I wrote this down here. I gave you a hint. Oh, right here. You want to go and put this data in the list in your calculator, stat edit, and go put all those 23 pieces of data into list 1. And so then you're going to do one variable stats of list 1 and make sure that the frequency is empty. So the frequency is blank, nothing there, no frequency. Okay, and then guess what? Look, I have this printout here. Hopefully I typed everything in correctly. Here is the printout the calculator gave me, and so look at that. There's the X bar. That is the mean of my 23 pieces of data. And look here, S of X. That is the standard deviation of my 23 pieces of data. So I took that 4.25 to get the standard deviation of the sampling distribution by dividing it by the square root of 23. Voila. Now I go do my t-score. X bar minus the mean of X bars over that standard deviation of X bars. That's 1.17. So when I go TCDF that with, don't forget the DFT, T, not Z, with 22 degrees of freedom, 0.1273. Is that unusual? No. That sample could be because of sampling variability. So do I have evidence to reject the null hypothesis of 30 and say that the average speed limit is higher than 30? I do not. So my p-value is greater than the alpha. I fail to reject. So there is not evidence that the average speed of all such cars on Thomas Lane is greater than 30 miles per hour. So do the police need to do extra police cars out there on Thomas Lane? No, they're good. All right, that's it. So good luck to you on your assignments, on finishing out some more problems to practice with doing your own dot plots to check for your son. Okay, all right. I will see you in the next video going over your assignment for day 2.